Hello and welcome to this video on rotational motion. Specifically today we're going to be talking about moments of inertia and rotational kinetic energy. Thus far we've had very good luck substituting rotational terms into previous equations to get new rotational equations. So let's talk about kinetic energy. Kinetic energy, EK, KE, K depending on your source, has the equation of 1/2 mv squared. According to rotational motion, if we take the translational velocity, Vt, to be equal to omega times r, we can plug this in and talk about the energy that this object has from spinning in a circle. We take that and plug it in. And we can apply it to a point particle, just a single point of mass just spinning in a circle with radius r. So we just plug it in. So now we have 1/2 m omega squared r squared. If we rearrange and solve, we'll get 1/2 mr squared times omega squared. And the v and the omega are roughly analogous. It's the linear speed versus the angular speed. What about this mr squared? Because based on how far or close you are from the point you're pivoting around, the point you're rotating around, the energy changes. Being closer to the source means you have less energy. It takes less energy to require you to spin. Being farther away means that you require more energy. But what about if we had multiple masses? Instead of just having one mass, what if we had, say, 3? In this case, each of these masses are spinning in a circle around the center point, but they're all different distances. So the 3 masses spinning, again, we're going to ignore the things that are tying them to the spinning part, would each have their own kinetic energy. This one would have a kinetic energy of 1/2 the mass times the radius squared times omega squared. This one would have 1/2 mass radius squared omega squared. And this one, again. The difference here is each of those different masses are different distances away. But because we know the radiuses, we can calculate that value. This one is a radius of 3 meters, this radius 1 meter, this radius 2. And if I were to say that the angular speed in this case is 3 rad per second, and these points had a mass of 0.5 kilograms, you could calculate the individual rotational motion of each of the points, or the total. Go ahead and give that a try on your own. Check back when you're done. Okay, if you did your math carefully, you'd find that each of the individual objects had the following kinetic energies, but that as a whole, they have the total kinetic energy of 31.5 joules. You'll notice that the spacing of the mass causes a notable difference between them. So this process works really well for individual points. If you only have 3 points, it works out pretty okay. What happens when you have more? What happens when you have something solid and rigid like a bike tire? Because these aren't point masses anymore. There are so many infinitely possible point masses, even in just like this area here, that you can't do this process. If we want to find the moment of inertia for an object that is solid and not made of distinct parts like the previous one, we need to add up all the parts. I being the symbol for moment of inertia. But that doesn't work here. Typically, what we would do at this point is we'd find a function to describe the mass and integrate over the function. However, that is beyond the scope of this class, and also people have done the work for us. Charts like this exist for the moments of inertia for various objects. A ring, which is what we typically treat a bike wheel as, if you rotate it through the center of the ring, has a moment of inertia of mr squared. Whereas, say, a solid cylinder or a disk would have 1/2 mr squared, because mass on average is halfway out. Of particular note, however, I want to point out these two. Both of these are thin rods, but one's rotating through the center of the rod this way, but others rotating through the center of the rod this way. The difference between the two of these is notable. There's a very large difference. This is 1/2, this is 1/12. Because rotating an object not around its central axis is a lot harder. Think about this tape. Rotating it this way, like so, is fairly easy. Getting it to rotate this way is a little harder, takes a little more work. And therefore, they'll have different moments of inertia. But once you know the moment of inertia of an object, you can calculate its rotational kinetic energy. We get a new equation. Instead of talking about mass, we'll talk about the moment of inertia because how far that mass is from the pivot point matters. Instead of talking about velocity, we talk about angular velocity, but it's the same equation we interacted with previously. It's still 1/2 mv squared, just what m and v are slightly different. So for any given object, we can now calculate its rotational kinetic energy. We just need to find its moment of inertia and the radius of the object. This equation is also on your equation sheet. It's listed as k equals 1/2 iw squared because the AP exam just says k for kinetic energy. But let's go ahead and use this for a second. A basketball has a mass of 0.5 kilograms and a radius of 12 centimeters. If I wanted to rotate a basketball with 2 pi radians per second, what would its kinetic energy be? Go ahead, give it a try. If you did your math carefully, you should get 0.057 joules. Give or take a little bit, which explains why it's so easy to put a basketball on your finger and spin it. And in fact, an actual basketball has a slightly lower moment of inertia than this, so it'd be actually even easier to spin. Anyways, thanks for watching. Have a good one.